On behalf of the Department of Zoology and Environment Sciences, let me welcome Professor Luís Ribeiro very warmly to our monthly guest seminar series. And I truly express my gratitude to you for accepting this invitation and taking out your precious time to deliver this lecture. Professor Luís is a senior researcher at the Forest Fire Research Center, University of Coimbra, Portugal. And he's going to talk today about the forest fires and the wildland-urban interface, fire behavior, safety, and lessons learned in Portugal. Luís holds a bachelor's degree in forestry from the University of Trás-os-Montes in Portugal, and then he holds a master's in social dynamics, natural and technological risks at the University of Coimbra in the same country, Portugal. So his areas of expertise include fires at the wildland urban interface, fuel management, decision support systems, and safety standards and rules in the firefighting. We asked him whether he's a firefighter. He said he's not, but he manages fires. So he has a vast experience in national and international research projects and published several papers and presented numerous communications, either scientific, technical, or operational in Portugal and abroad. Professor Luís, we are very honored to have you today, and now the floor is yours. And we know that the experience that you share with us today would be very valuable to a country like a tropical country like Sri Lanka. Thank you very much.
Thank you very much. It's me who is quite honored to be here and to have the opportunity to share with you some part of what we do here at the University of Coimbra. So let me just. So please tell me that you are seeing the correct screen. Sampat, yeah?
Yes, we can see you, we can hear you, and very well. We can see the slides as well.
So I already started by thanking you, and it was almost a surprise to me to receive your emails, as I already explained. But it's with great pleasure that I'm here today to talk to you a bit about forest fires, the wildland urban interface, fire behavior, and so on. And so I will start with my first slide. What you see there is Coimbra, the old part of Coimbra, namely the university. This is the university which about 2 or 3 weeks ago, the university got 732 years old. It's one of the oldest in the world, the second oldest in Europe after Florence in Italy. And what you see is not Coimbra burning, although it seems. It's actually a forest fire burning about 2 or 3 kilometers to the east of the city. But this is a perfect illustration of how close fires can come to the cities and what the dangers are, not only because of the fire itself. And I come from the Forest Fire Research Center, which is these initials SAIF in Portuguese. And this Forest Fire Research Center is a unit of ADAI. ADAI is a non-profit organization with public utility, declared by the government with public utility, that belongs to the University of Coimbra, namely to the Mechanical Engineering Department of the Faculty of Sciences and Technology. And all our activity is basically devoted to applied scientific research and to the ways that we can connect this applied scientific research to the community. And this is done basically through services and consulting, to training of operationals and the population itself, and development and testing of solutions for wildfire prevention, management, or fighting. This is basically our association. I am talking to you and showing you part of the work that we do, but I'm not responsible, of course, for making all of this. This is part of our team, the main researchers from our team. This is Professor Domingos Viegas, which is our director. He is one of the most prominent world-leading scientists in the area of forest fire research. He's the founder of ADAI and also of SAIF. And this is just a collection of images of what we do inside our laboratory. This is our forest fire research laboratory. It's the largest one in Europe and one of the largest ones in the world, and is fully dedicated to the research in forest fires. We have a lot of structures inside the laboratory that were built by us. Some of them, we designed them in order to address specific issues that we wanted to study. And you can see that we address several topics related to fires, and most of them to the wildland urban interface. You see here the problem of tents and camping caravans and so on. We are also testing different solutions for the protection of persons and structures. We have connections to the industries where we perform several tests, all of them connected to the forest fire research. So, going to the topic that brings us here now that the introduction is made. The genesis of our team and our main motivation was understanding that studying fire behavior and understanding how it works may give us the possibility to contribute to the improved safety to anyone that faces a wildfire, being a firefighter or a forest guard or a civilian or whatever. Because we have been seeing that most accidents that are that have some relation to forest fires are due to insufficient knowledge of how a fire behaves, how it propagates, how it goes. And people often get entrapped by fire because they cannot anticipate what fire can do. And this is a continuous learning process, like in many other areas of engineering and on civil society. We learn from mistakes. And we can say that the bad things that happen to some people may be the salvation of others, because if we study them and analyze what happened, we may be able to find ways to avoid the same mistakes. And that is a large part of our work, to study what happened in real scenarios, in real cases, especially when there are victims involved. This is just a collection of the cover of some, on top, those are official reports that were commended to us by the Portuguese government to study and analyze large fires in Portugal, especially when there are deaths involved. And the year of 2017 was particularly bad, as I will show in a couple of minutes. And on the bottom, it's just an example of books and reports that we produce, some of them in Portuguese, some on English, some are more of a scientific character. Some of them are intended to be read by the population in general, but this is a large part of what we do. And the same way as in other cases, the learning of safety rules or their implementation is a reactive process and is a slow process. And it happens only in most cases because something bad happened. You can make a parallelism to the aviation or to, for instance, the safety belts in the cars. A couple of decades ago or a few decades ago, cars did not have seat belts. And then we started seeing people get hurt and die because when they had a crash, they would go out the window or hit the wheel or something. And then we implemented seat belts, but seat belts were not mandatory. So people would not use them because it's a mess, putting the seat belt on and so on. And accidents would keep hurting people and killing people. And nowadays, my car will not move if I don't put the seat belt. It's an automated reaction that for me is almost instantaneously as I enter the car. So this is a reactive process when something bad happens, when accidents happen, and we tend to study what happened to try to change it. And this table shows you some of the most infamous wildfires that killed people. They are all in the United States, but that led to the implementation and to the creation of different things that completely changed how fires are dealt with today in the entire world. For instance, this first one, the Man Gulch fire, 70 years ago, killed 13 persons, 12 of them from an elite group, the Smoke Jumpers, that was recently created in the United States. And this accident led to the creation of laboratories and research programs. These laboratories created in the United States are still there, and they are still on the lead of the forest fire research all in the world. One of them, the Missoula Fire Lab, is probably the most well-known fire research laboratory in the world. Then other things happened. For instance, these 10 standard orders or watch out situations that came as a consequence of these two accidents are nowadays implemented in the firefighter training all around the world. In Portugal also, and in many countries in the world, in their doctrines, in their trainings, they implement this set of rules. Then the personal protective equipments were also developed because firefighters were getting injured and burned because they were using regular clothes, clothes for working in the woods, and not specifically protective equipment. So they were developed on the aftermath of this fire. The Americans also developed a fire shelter, which is some sort of an aluminium sheet, more or less. It's mounted like a tent, and in case firefighters get entrapped by fire, then they can deploy it and protect themselves. They can stay there for up to a minute or so, and probably can save lives. The problem is that it was not mandatory, and these three guys died because they were entrapped and left their fire shelters in the truck. So after this happened, the US government made mandatory the use of fire shelters. And then the LACES protocol, this is also used all around the world. So you see, only after something bad really happens, we tend to take actions. And this is something that we take very serious, because we have implemented or helped implement several changes in the Portuguese agencies, namely in the training of firefighters. And throughout the history, there have been several studies about what happened in accidents, mainly started in the US. Now our team does this very regularly. We have studied all accidents that happened in Portugal. And one thing, and there are a lot of things that we can see in common in different accidents. One of the most dangerous things is when the topography forms what we call a canyon. And a canyon has two valleys with a certain degree of inclination that join together and have an upslope here on the waterline, either with a curve or without a curve. And these kind of situations are responsible for lots of accidents and lots of deaths. Usually, when you have accidents with groups of people getting killed, it's a situation in the topography like this. This is one of the latest ones in the US, and probably the one that killed most persons. So there was a fire here, and the hotshot crews that are firefighters that go walking with hand tools to fight fires, they were here. They saw that they were not safe. They went to a part that was already burned, and still today we don't know why they decided to come down here and come to this ranch. They felt that they would be safer. So the fire was there's a mountain here. They started coming down. What they didn't see was that the fire turned around this mountain and caught them all by surprise. So all 19 of them, they had 2 minutes to deploy those fire shelters, but it was not enough time, and they all got caught there. But this happens in a lot of places also. For instance, in Spain here, we studied also this fire. Firefighters were up there just parking their cars to fight the fire that was on this side, but then fire jumped to the bottom of this canyon, went up, and even before they started to do anything, they got caught by the fire and 11 died. Also in Portugal, we have several cases in the same situation. And it doesn't need to be a hot summer day to happen. So this one happened during the winter. There were 5 degrees temperature, was cold, but the relative humidity was very low. And the same thing happened. You see a fire truck there. It was just for the reconstruction, for the photography, but it's the place where they got caught. This is just 50 or 60 meters, and fire went up and caught 4 professional firefighters. So I showed you images. Now I can show you some common points that have been found in 50 years of analyzing 222 deaths among firefighters. And strangely or not, this happens in relatively small fires or isolated sections of large fires. If you go to a fire and you see large flames burning the trees, the grounds burning, you get scared and you don't go near that. But if you are in small fires or in a fire that goes in fine fuels, in herbaceous or in small shrubs, you get more confident. And sometimes these fires also have enough speed and intensity to catch people unnoticed. This, to the sudden changes in wind direction and increase in the fire acceleration of the slope, up to this time were considered as a surprise. But nowadays we know it happens. And it happens all the time, and it happens because fire itself creates these conditions. So what was early a factor of surprise for the firefighters nowadays is something that is taught in the training of the firefighters, and mostly because these things get analyzed and studied. So in more recent years, you see 16 years of analyzing 310 deaths. So it's coming from 50 years to 16, but that's increased because now we have different things in the equation. So we have accidents with vehicles. Almost half of the accidents, this is in the United States, okay, were related to accidents. And then the lack of physical conditions. This is something that we are dealing with nowadays in all kinds of the sectors, in all sectors of our society. The lack of physical condition that provoked some heart attacks. So as I told you, here in Portugal, we have inventoried, as far as we know, all deaths related to firefighters, at least those that we could find. And we have visited, well, in the time or in the period that we have been working in ADAI, or that ADAI exists for 30 years, more or less, we have visited and studied all the accidents related to forest fires. And if we analyze the type of activity that the victims were having during the fire, we can see that almost 60% are related to the wild and urban interface. And this is a clear evidence that shows you that the wild and urban interface is a very noticeable problem and something that we really have to attend to. So coming to fire behavior. It's essential to know how a fire behaves if you are in somehow or some way of your professional or personal life expecting to deal with a fire at some point. If you live in an area that is fire prone, or if you work in something related to fire, it is essential that you at least know some basics of fire behavior. And this is true to what I just said, but also to plan and manage the land around our homes. Because we need to understand that fire is not like an avalanche or a fast flood. It doesn't go indiscriminately taking everything on its path. Fire only propagates if it has fuel. So managing fuel can mean saving our home. But coming to the basics, how does a wildfire propagate? Any fire, being wildfire, residential fire, any fire, is subjected to what we call the fire triangle. And the fire triangle means that you need three things to have a fire. First, you need a source of ignition, okay? You need some heat. Then you need some kind of fuel to burn. And in the last thing, the third point is oxygen. You can't have fire if you don't have one of those three. Then coming to wildfires, we have what we call the wildfire triangle, or the fire environment, and this is composed of these three things. That is, a fire to burn needs fuel, in this case wildland fuel, because we are talking about wildland fires, wildfires. Then fire propagates in a certain topography, and it's mainly driven by slope, and it is subjected to the influence of the meteorology, mainly the wind speed and direction. So those are the three components that determine how a wildfire propagates. But throughout our investigation, and I gave some hints before, we have seen that fire behavior is not static. It changes with time. So you see, this image is one of our combustion tables in our laboratory. Those are pine needles, maritime pine needles, and we placed perimeter ignition in a square, as you see. This is 3 by 3 meters. And nothing else, nothing is changing. We don't have wind, we don't have slope, the fuel is the same, so nothing is changing except time. We let it burn, and from 20 to 30 centimeters of flame height, you will go to 3 or 4 meters of flame height, and nothing has changed. So the fire itself changes its characteristics, and it feeds itself in the combustion reaction, making it more intense. And this can tell us that if you have that common fire environment triangle, you could expect normal fire behavior. But when you had the time, if time passes and the combustion remains, you can expect extreme fire behavior. And a very clear definition of extreme fire behavior made by our director, Professor Viegas, is that it is characterized by a set of characteristics and properties that prevent its control and suppression in safety and with the available resources of knowledge. This is important because what we think it's an extreme fire today may not be an extreme fire 50 years from now, because we know for sure that nowadays we can fight fires that were impossible to fight 50 years ago. 50 years ago, we didn't have air tankers, we didn't have helicopters, we rarely have heavy fire trucks to fight fires. So fires were fought with hand tools, with buckets, with the incredible courage of many people. And at that time, we could probably fight fires up to 500 kilowatts per meter or something like that. And nowadays, it is knowledge that the linear or the limit, the thresholds of the capability of humans to fight fires, it's around 10,000 kilowatts per meter. So after this, it's virtually impossible to control a fire. So that's why it's important to say the available resources and knowledge. Who knows what the future holds us. And briefly, let me talk to you a bit about these cases of extreme fire behavior. It's possible that we may find others. Actually, our team was responsible for introducing in the scientific literature the terms eruptive fire behavior and junction fire or convergent fire fronts. The phenomena was, I more or less identified, but it was our team that characterized it and proposed some models to try to model how these things happen in nature. So just some examples. The eruptive fire behavior is that's related to the canyons that I showed you some examples before. So you see, this is an example of a simulation of an accident that happened here in Portugal in 1985. The fire was propagating, pushed by wind from left to right. And then the wind doesn't change, but the terrain does. And if you notice carefully, this is 15 times accelerated, and the fire to propagate here horizontally without slope, it takes around 6 minutes to reach the base of the canyon. Okay, so and it reached the base of the canyon pushed by the wind. And as soon as it enters the canyon, it takes 1 minute. It's 6 times less to go all the way up the canyon. So a team of 14 firefighters was coming down here. They didn't see the fire. It was coming down to help some people that were screaming here in the nearby village. And as they arrived the middle of the canyon, the fire reached the bottom and it went up and it killed them all. And I'm sure you understand and you know that it's logical to say that fire runs faster uphill, but humans run slower. The deepest the slope, the slower we can go, especially if we go with heavy equipment on our back. The second manifestation of extreme fire behavior is the ground fires. It can be of different ways, either active or passive. It's quite impressive. It causes large destruction. In terms of safety, this is not one of the major concerns because no one will go face a fire that is burning the crowns of the trees. You will not, you can't virtually do anything to stop this. You just need to wait for better conditions. It has large flames and very, very high intensity. One of the major issues related to ground fires is that when trees burn, there's a high probability of burning embers or burning particles being released from the fire and then traveling in the wind and causing spot fires, meters, hundreds of meters, even hundreds of, even tens of kilometers away from the main fire. This is another manifestation of extreme fire behavior, what we call spot fires. Spot fires are created from burning embers that come from the main fire front, get elevated in the plume of the fire, and that travel with the wind, go fall in some place far from the main fire, start another fire, and then maybe or probably, if it's close enough, it can merge with this and create another problem. You can see the pictures taken by us here in a fire near Coimbra some years ago. And from the first picture to the last one, it's only 2 minutes. So you see if someone was there trying to fight that fire and didn't see those particles falling on their back, this quickly evolves to a large fire and people could be trapped there. So that's one of the major issues concerning spot fires, is starting fires unexpectedly in some place that cuts firefighters unattended. Another one is the jump fire or convergent fire fronts. We have called it jump fire or junction fire because of the high velocities and intensities that it can reach in the intersection of the two main fires. This was brought to us by a real fire that happened in Australia. The Australian government asked our team to serve as experts in analyzing this fire and trying to see what happened here. And we saw that the proximity of this North fire and South fire, the McIntyre and the Bendora, the proximity of these two fires led the central one, after it started, to reach incredible speeds, velocity, something like we have never seen. And so we started an experimental program with different angles, different combinations of slopes and angles to see what happened. This is an image in the visible range, and this is in the infrared. Here you can see how this goes in terms of distance and time, and here in terms of rate of spread and time. There's a very sudden acceleration at the beginning. The fire reaches incredible speeds and intensities like we haven't seen in any other fire, and then it's more or less stops in the same values. And last, the fire vortices. Some spectacular images are seen on the TV every time there are fires, mainly in California. We are used to see this. We have an experimental device that allows us to change the velocity of the circulation, and we can see different configurations and what happens in the fire. The trajectory of a fire vortice is almost impossible to predict. It's like a tornado. You know that there are certain conditions that induce its formation. It's basically when you get a hot air mass meeting a cold air mass. So there is a force to rotate and go up. This happens in cyclones, tornadoes, typhoons, and also in the fire vortices. But we have found that not only vertical structures can be found in fires, also lateral structures, and mainly when there is a hill, you have fire going up one hill. This is a real case scenario, this is simulation. So the fire goes up the hill, and when it reaches the top, it's pushed by wind, it tends to spread laterally. So it goes both ways, expanding its perimeter, and then starts descending. So, and this is due to the lateral vorticity that is formed here on the ridge of the hill. So not only vertical vortices, but also horizontal structures. So I've shown you some extreme fire behavior manifestations. How to connect this to wildland urban interface, there's a scheme that was proposed by one of the most famous scientists in these topics, an American scientist. And if you have severe wildfire conditions, either from fuels, weather, or topography, or the combination of the three, and if you have ignitions, it's probable that you could expect extreme fire behavior in the wildland. So with extreme fire behavior, if in the wildland you put homes, there's a probability of having residential homes in the middle of that wildfire. And if those homes are not resistant, you can have a lot of homes burning. And if you have a lot of homes burning, there will be never enough sufficient protection firefighters or trucks or whatever to attend to all. So we could face a potential wildland urban interface fire disaster. And this can happen basically if two things exist: fuel and weak resistance from the houses. And that's namely where we can act. First, to make our houses more resistant, and then to manage the fuels around our houses. That's the only way we can stop this sequence of happening, because we cannot interfere in the weather or in topography or in the extreme fire behavior. So making our homes resistant and managing the fuels around it is the only way we have. I've been talking a lot about wildland urban interface, or WUI. If this was a class or a presential training, I would ask you if you could tell me a definition, but to be faster and quicker, I can tell you that the best definition I've found so far of wildland urban interface is that it represents the physical space where we have people, vegetation, and structures, and in a fire-prone environment. That means if you have vegetation in some place that can burn from a wildfire, and in the middle of the vegetation you put houses and people, then this is considered the wildland urban interface. You see two images from Portugal. Actually, Portugal is a small country. It's larger than Sri Lanka, but it's a small country, and we have a lot of house dispersion in the country. And usually the problems in the interface arise, especially when we have extreme fire risk conditions. You see here, whenever a fire approaches a house, all firefighters go to protect people in the houses, and they leave the fire unattended. So whenever, and you see here, there are 2 trucks with 10 firefighters to protect the house that would basically be safe by itself because it has no fuel around it. And at least in Portugal and in many parts of the Mediterranean basin, but in many other parts of the world, there are several factors that contribute to the increment of the danger in the wildland fire urban interface. So you see, nowadays people tend to go to the large cities in search of jobs and the better conditions of living. So the large cities here in Portugal are almost all near the sea, in the coast. So the interior region gets depopulated, and the ones that stay there are getting old, they are getting aged. And the main consequence is that there is a lack of manpower to manage the fields, especially the fields around the houses. And so vegetation starts to approach the houses, and if in case there is a fire, the danger is obviously higher. The other two are also closely connected. For instance, this great demand for housing in the main cities makes that people travel to the cities, but they keep their home houses in the interior. So the houses from their parents or their great parents that are still in the field, and they don't sell them. So they like to go there on the weekends, but they go on the weekends, they are not there during the rest of the year, so they don't manage the land. And when they go, they put themselves in danger in case there is a fire. Also, in the large cities, the increment of population needs to be accompanied by an increment in housing. So if there is no more space inside the cities to put houses, to build houses, these houses need to be built on the outskirts of the cities, and many times putting houses in the middle of the forest. So this gives a huge boost to risk in the wildland urban interface risk. And this risk can depend on a lot of things. The risk can depend on the fuels, the natural fuels, the road network, the topography, the infrastructures, etc. Let me briefly tell you a bit about all of these. So the fuels is obviously the most important one because it's the one we can manage, and this has a great impact on the survivability of our house. Then the road network is also important for several reasons. For the firefighters to reach a settlement, if the roads do not allow firefighters to go through, they will not go. But also on the opposite direction, if it's necessary to evacuate a settlement, people need to pass safely through these houses, through these roads, and they can help create discontinuities in the landscape. But of course, if they are too narrow and there is not some kind of management around them, which is mandatory by law in Portugal, this doesn't create much of a discontinuity. You can see fire doesn't stop here in this small road. Then the topography. The topography is one of the most obvious factors also. It's quite different to have a house on the bottom of a valley, on the middle, or on the top. You see the canyon configuration that I talked about in the accidents part, and some houses on top. This is a potentially death situation. If there is a fire here, houses are very much in danger, and also the people inside. The infrastructures are related to support infrastructures that can help firefighters fight fires, but also to other things that we build, like transportation or energy that can be a source of energy, not in ignitions, not in this case, for instance, because there is fuel management below the line. This is also mandatory by law in Portugal. But in some cases, the existence of these things can help or increase the danger in case of a wildfire. Then the self-protection, which is something that we are taking very seriously today. Even our government is implementing some specific measurements regarding this passive self-protection, mainly through fuel breaks that are mandatory around the houses and around the settlements, but also alternative land uses, the good choice of species for the gardens, etc. We also have active self-protection mechanisms, and we are studying a lot of them in this Fire Protect project. You can check the link if you are curious on knowing what is being tested and developed. It's based on water sprinkler systems or canyons or special covers that can be put in houses or communities or whatever. The last point is the ignitability of buildings. And this also depends on a lot of things, and is directly connected to the probability of a house being saved or not during a wildfire. In heat transfer, we have three mechanisms, or basically three mechanisms. You have the convection. So imagine you have a fireplace. If you put your hands 1 meter above the fire, you will feel the heat and you can heat your hands. That hot air that comes from the fire is the convection. If in the same fire you put your hands laterally, it means not above the fire but laterally, you don't feel the hot air, but you feel the radiation. That's the second heat transfer mechanism. And then you have the conduction. The conduction is, we don't care about conduction in terms of igniting homes, but it's, imagine you have a fire stick, you put that fire stick, you ignite the fire stick and you put it vertically. The only way that fire has to consume the fire stick downwards is by conduction. But actually the mechanism that is responsible for the most ignition of houses is this transport of burning embers. So you can see on the left is a test in one of the American labs that I talked to you about, and on the right is a real scenario from a fire in Canada some years ago. This shower of burning pieces of leaves or branches, twigs or something, some natural element, these burning embers are responsible for most of the house ignitions because they can land in different vulnerable parts of the houses and ignite some components. We have performed some tests. So this is one of the wind tunnels that we have in our laboratory. This is a particle generator up here. We have constructed a section that would allow us to drop burning particles here. We have built a house or a room to scale here with a window that is open to a quarter. It could be a window that you leave a bit open during the summer to get some air in the house, or some window that it's broken. And then we have an inside door that can go to the corridor inside the house. And we tested 3 scenarios with the door closed, the door half open, and the door fully open. We wanted to test what is the influence of opening or not this inside the door in the movement of air and particles. So you may know that the wind or the air goes from high pressure areas to low pressure areas. This is true in the meteorology. You see the high pressure areas, the wind tends to rotate and go to low pressure, but it's also true in other aspects of our life that you may not be aware. For instance, in the surgery rooms or in the factories where the electronical components are made, the rooms are kept pressurized so that the pressure inside is higher than the pressure outside. This makes the air go out instead of in, and with the air goes the dust. And having dust-free areas in the surgery rooms or in the components mounting rooms is very important, as you may imagine. What we noticed here is that when the door was completely closed, we had a difference, a positive difference of 1 Pascal inside. So the pressure was higher by 1 Pascal inside the house, the room, than outside. As soon as we opened the door, this differential inverted and 6 times higher. So the pressure was very much higher outside the house than inside. What does this mean? If you remember what I said just a couple of minutes ago. When the door is open, the air tends to go around the house. As soon as you open, the air tends to get inside the house. And with the air, during the firefighter, goes the burning embers. And we have measured with a PIV system. It's a system with very high-speed cameras that allows us to count every particle that passes per second. And you see, with the door fully closed, so no opening, we have around 3 particles per second entering the room. As soon as we open it, it goes to 3 or 4 times higher. It really doesn't make much of a difference if you have the door half open or fully open. The important thing is that the air is forced inside the house. Why is this important? During firefighters, when there is a need to evacuate houses, usually we say, leave the outside door unlocked so that, closed but unlocked, so that in case of emergency, firefighters can go inside and pick you up. But there is never recommendations regarding the inside doors. And with this, we have been able to advise people to leave all the inside doors closed, because even if you break a window, there is a lower probability of the air and the burning embers entering inside your house. So this was the point of this test. Other tests that we have done is with the window shutters, the blinds. So this is a PVC blind, but we also tested aluminum and wood. And you see the PVC degraded very easily at 150 degrees. The combination of blinds and windows, especially the 2-pane windows, not with 1 glass, but with 2, they are very efficient in protecting from fire, but the PVC windows not. Also, another project that we are working on that recently just finished, we analyzed the micro scale of the house plots. And one of the things that we were interested in was the vegetation surrounding our gardens, because a lot of times we don't have fuels inside the cities, but we have a lot of garden fuels, if you want to talk like this, if you want to call it this, the green edges that are of different species. And this is sufficient to take fire to the houses. Although there is no other vegetation, as I told you, fire can come from burning embers, land here on these green edges and take the fire to our house. So what we wanted to do is study, in this case, 4 species. 3 of them are conifer, one is a broadleaf, and we characterized it in very detail. And we made tests with three trees and 1 isolated tree. You can see an example of a test with the broadleaf and the conifer, and you immediately see the difference. Although they are very young trees, not like sometimes we can find in our gardens, which are old trees, more dense with more fuels, and you can immediately see that this burns like gasoline almost. So it's very dangerous to have this kind of green edges near our houses. In another project that is currently going on, this Safe House Refuge project, we are testing with many different species that are usually found in our gardens, even with the fruit trees and with ornamental trees, with all of that. We are testing the same, and we are getting similar patterns. Some species are more dangerous than others, but yeah, this is an ongoing work. In this house refuge project, we also did something quite interesting for Portugal. I'm not going to bother you with much details of this, but we analyzed 2,000 isolated homes in Google Earth, analyzing what's in the surroundings, giving this a class of risk from low to extreme. And we could compare all 18 districts in Portugal in terms of fire risk in the wild and urban interface regarding the proximity to fuel. So in terms of average, we would say that in Portugal, we are not so bad, but in fact, this is due to a couple of districts that are clearly higher or more safe than others, because in terms of mandatory regulation or legislation, 70 or 80% of the districts don't follow those rules to the letter. Now, another part that I want to talk to you about is some examples, and this is the final part of my presentation. So we have seen different cases of fires in the wild and urban interface in the world in the past years. Probably in the TV you have seen images from a lot of them. This is Australia, that in several years they had problems with fire, but also with smoke. You can see here the theater in Sydney, it's almost not visible because of the smoke. This has serious implications in human health. In Canada, the video I showed you earlier in Fort McMurray, but also these pictures, Chile, where this is not Chile, this is Greece. In Greece, at least in 2018, 80 people plus were killed in Mati in a single, not so big fire accident in the wild and urban interface. The United States have shown us pictures every year. They have pictures with problems of fires in the wild and urban interface. They have a serious issue that is related to the type of materials they use in construction. As you may know, a lot of houses in the United States are burned with the combustible materials, namely wood, something that doesn't happen in Portugal, but in Portugal we also have had serious issues. This is an image that was shown in 2006 several times in the media, is Funchal, the capital of the Madeira Island, which is basically a touristic spot. It's not in Portugal mainland, it's in the Atlantic. And the fire was north of the city, but the wind was pushing the smoke throughout all the city. Actually, due to embers, you see this is the urban perimeter, the flying embers that came from the fire on the north burned several houses in the historical center here in the middle of Madeira, very near the sea. So not near the forest, but inside the city. And then in 2005, I'm talking to you from here, where this lie is one of our laboratories. Is not the Forest Fire Research Laboratory, but it's our headquarters. And these are city forests, city parks, and they were burned in 2005, where this fire reached the outskirts of the city. And then in 2017, of course, in June and October, I don't know if you've heard, but this was the worst here in our history, especially in June. We had 120 deaths in these two episodes, and in a single fire in June, 66 persons died here in Portugal, and I will talk a bit about that. So this is another work we've done concerning the identification of the fire risk in the wildland urban interface in Portugal. You see, this is where the risk manifests the most here in Portugal. And actually those fires in 2017, both in June and October, burned all these areas. So In June, the Pedrógão Grande fire had more than 40,000 hectares burned, and in October, more than 200 hectares burned in one day here in the central region, mainly where there's a high risk in the wildland urban interface. So I have a couple of incidents or accidents here, but actually I'm just going to talk about Pedrógão Grande because I don't have the time to talk about all the others. And this Pedrógão Grande was the most infamous fire we had in Portugal ever. One of the fires that the Portuguese government asked us to study, and we produced a report, a very detailed report for this. It's actually not just a fire, it's a complex of several wildfires that merged and formed this shape. And this was called the Pedrógão Grande Fire Complex, but it's a mixture of several, a merging of several wildfires. It was basically burning for a week, but the first 2 days were the crucial ones. So most of the area burned in the first 2 days, especially in the late afternoon of the first day, where almost 9,000 hectares burned in an hour. It's 3,000 hectares per hour, which is something very rarely seen in wildfires. And this is particularly, especially in, or mainly in the area where most accidents and destruction was observed. So 66 deaths, more than 1,000 damaged or destroyed structures. And as I told you, we did an analysis, a very detailed analysis of everything that happened on that fire. And it covered the fire propagation, how it started, how it developed, how it ended up with that shape, what the fire burned, how the people or the persons were killed by that fire, and what was the damage caused in the structures in the area. And with this, we analyzed this individually, but then at the end, we managed to merge all this information and come up with an index of the impact of this large fire in the communities. And it was possible to map that index. So first, the work on the structures. This part is the Pedrógão Grande part, and this part is the Góis part. Although it merged, in this part the destruction was not so high, and actually we didn't have the resources of the time or the time to go look in this part. So we focused where the killings and the destruction were higher, and we visited every single structure, being a house or not, that was affected by the fire. So we went there in the team, we talked to the people, we tried to understand a lot of parameters that we identified previously in the database. And we had a questionnaire that we could go with our mobile applications and start filling with all the description of each structure. So this is a density map of the destruction in structures. You see, mostly concentrated here. It's also where all the deaths happened. It's in this area. Quickly passing through the main results, which is interesting and goes to corroborate all that I've said to you before in the previous slides. So the type of structures affected were mostly support structures, sheds, storage, outbuildings, etc. But 25% were houses, either permanent houses or secondary houses. Almost all of the victims of these fires lived in the large cities, like I told you before, in the large cities in Lisbon or in Coimbra or in Porto or Braga. And then they had the house from their old grandparents or parents in this area, and they came for the weekend or for holidays, and they got caught in the fire. So this is truly an issue when managing land and the movement of people. Almost 86, almost 90% of the constructions were of advanced age, which explains its lack of resistance. And basically the construction was stone and concrete. So in principle, the houses should be resistant, but they had several weaknesses or vulnerabilities that led to their destruction. Then what I've shown you as the main mechanism of fire ignition was seen here. So you see, spotting or burning embers were responsible for burning more than 60% of the houses. Then the direct fire impact in 21. But You have another class that is the materials burning in the vicinity of the house or next to the house, and with a high degree of probability, these materials got ignited by burning embers also. So I would say that you could merge these 13 with these 61 and see that the burning embers are in fact the major cause of ignition in the houses. And the location of the ignitions is mainly in the roof. This is due because we have, there are different types of construction, but mostly in these old areas with old houses, you have a wood structure supporting the ceramic tiles. And the ceramic tiles have openings between them. So the particles, the embers, can very easily fly through those ceramic tiles and enter the houses, the attics and so on. Then what you have inside may be flammable and it can ignite, and then the wood structure gets destructed and the roof falls on top of the house. So this is related to the structures. The other part was related to the fire itself. And we were concerned about the destruction of the income resources of the landowners. For instance, the destruction of agriculture fields or the pasture for the animals or even the forest. This causes a high impact on the people that live here, because in some cases they live on the income that they can get from these activities. And this is based on data provided by the European Union Copernicus service, which is a service that helps countries in cases of disasters. And they analyzed the satellite images after the fire and said that, well, almost half of the area got probably entirely destroyed, only 35% being moderately damaged. And the third thing was the deaths, the accidents. So almost all happened in the end of the first day of the fire. So 66 persons died. They did not die all immediately. Some died afterwards in the hospital, but all consequence of the fire. And in the next day, early morning, our team was already there, providing our help to the law enforcement, to the police, to the firefighters, to whatever we could, even without the mandate from the Ministry of Internal Affairs, because afterwards, when they asked us for the report, they gave us an official mandate to go question everyone and to do all the diligence that we needed to study all these cases. So there were 65 civilians dying, 1 firefighters. There was a stretch of 400 meters of road where 30 people died. This was afterwards known as the death road. A lot of accidents, some trees fell on the road. With the smoke, you couldn't see anything. So families trying to run away from the fires died here in the road. Only 4 people died inside their homes. And these 4 people had some kind of vulnerability. 2 of them were a very elderly couple, almost 90 years old, that had serious problems in moving. Another one was a blind lady that couldn't leave her house. And another one was a citizen with mental issues that also couldn't leave the house by himself. And we have seen many, many houses from all those victims that stayed in perfect conditions. And this means that if they did not run, if they had stayed in their homes defending, they would probably not have died. And that's one of the messages that we try to pass, is that if you are fit enough, if you are strong, if you are mentally capable of defending your house, and if your house has the conditions to be defended, this means if it's more or less resistant and you have taken care of the vegetation around your house, you should be able to stay and defend. But in this case, these people got scared with the fire and the noise and the wind and so on, that they tried to run, but the fact is that they got caught. So at the end, merging all this information that we collected for 2 or 3 months, I don't remember exactly, or 4, it was a huge task in such a short amount of time. So we managed to produce a simple, very simple mathematical model where we attributed weights to all these variables. And then we managed to map all these variables and have partial impact maps for the structures component, the burnt area component, and the victims component. And at the end, merging all of this allowed us to visually see where did this fire mostly impacted on the community. You see all these dark points or black points are settlements or villages. The large ones are large cities. So Coimbra is here on the north, it's outside, well, it's actually here. I'm here, this is the Mondego River, this is Coimbra. So you see, it's not very far from us, but as you can see, there is a large dispersion of houses over here where the fire had its most extreme behavior and the most destruction. And afterwards, I already talked to you about this. So some lessons we learned. This was one of the most serious accidents in Europe, the most serious here in our country. And the most damages and accidents were concentrated on a small part of the fire where the impact was, of course, higher. And what we have seen is that the population, the majority of the population at that time, and probably now, although we are trying to change this, population is not prepared to react to the arrival of the fire. There is no preparation, no knowledge, no information to the people to what should you do in case of fire. There were no information. What should you do in case of fire reaches your home? Now, after that, we have started with different governmental programs to have more information to the persons, to have training sessions in some interior village and so on. So we are trying to change this a bit, but it's still not perfect. So most of the structures were of advanced age and were supporting structures, sheds or barracks or garages or whatever, old buildings. But even so, 25% were homes. And this is very, very important because many people did not have insurances on their homes, or almost all. So there are no insurances that can give you back your money or the money for your house in case of a forest fire. And so the government had some money put into helping these people. 60% of the structures were burned due to those flying embers or projections, and mainly through the roof. As I said, houses can be a safe place as long as they or their surroundings are kept in good conditions, and as long as the ones or the people that stay there are physically and psychologically able to defend their houses. Something that is very, very important is that if you need to evacuate a settlement, a village, a city, whatever, you must plan and do that in advance, way before the fire is going there. Because what happened here in Pedrógão is that evacuations were made when the fire was reaching the houses. And this is not called an evacuation. This is running away from the fire uncontrollably. And so the potential to have an accident like we had is huge. And that's it. Some, well, pictures that came from the media at the time. You see houses being destroyed. That elderly couple of almost 90 years old died in that blue, that's the house with the blue circle. And you see the level of destruction was huge. I couldn't finish this presentation without telling you that we are organizing probably the most well-known conference in the world related to researching forest fires. It's here in Coimbra every 4 years. We organize this every 4 years, and we get to reunite here all major scientists or all relevant scientists in terms of forest fire research in Coimbra. From all over the world they come here. And incredibly, and we were getting a bit worried because of the pandemics and the war in Ukraine. We were thinking that maybe this year will be a bad year for the conference. People are afraid of coming. And incredibly, we had way more submissions than in the last conferences. And we don't have the space for so many submissions. And this means that the world is tired of staying at home. And we want to meet again outside Zoom Although with you guys it would be impossible, thank God for Zoom, but we are actually missing now the opportunities to get together again. And our conference will be a very good opportunity to meet again. So that's it. I finish here. I hope it wasn't too boring or too long. Sorry for passing my time, but now feel free to ask any questions that you wish. Thank you.
It's a completely new area for us. I think most of the audience never heard anything what you you explained before, and it's almost like a safety lesson. Forest fire has never been forest fire has been a big problem in Sri Lanka in certain areas, but the safety and fire related deaths, that sort of things are relatively less common here. But this is really great. Thank you so much for a very exciting presentation. Now the floor is open for questions. One question came to me is that you showed these model fires in your laboratory, which are really fascinating. These small fires that you showed and how it burned and what it does. So my question is: are these is a small fire? Is it exactly scaled down version of a large fire, or large fires behave differently compared to a small fire, like a tiny fire in the laboratory?
Yeah, well, we do those scale fires up to scale. We also do some tests in the field with real fires, but statistically and in engineering, you have ways to compare small scale experiments to large scale experiments. So we always have a way of comparing this. May not be exactly the same, and mainly because of the distribution of fuels or the homogeneous conditions, but having this in the laboratory with controlled conditions allows us to eliminate all externalities that we cannot control in forest fires. So we can focus on wind, changing the wind and maintaining everything else constant, or simply changing the slope or changing the fuel. So, but yes, we can relate this very easily to what happens in reality.
Awesome. Okay. In Sri Lankan, folk, it says that never underestimate the size of a snake, a priest, a princess, prince, and a fire. A small thing can also be very dangerous. Anyway, yeah. So the floor is open for questions.
Professor, can I ask a question?
Yeah, go ahead. Yes.
In addition to the awareness program, what are the pre-planning you are recommended to face this situation?
Okay, so we have by law, we have to take care of the vegetation around the houses. So basically our pre-planning focus on two things. On one side, the awareness programs on training people on how to react in case of a fire. And we have implemented a program on the aftermath of the fires of 2017, the one that I showed you. We have a program in several villages, from small villages from the interior of Portugal, that is training them, having someone in charge of reuniting the people, having some safe places to go, some escape routes, and so on. And then on the second part, and by law, this is mandatory by law, there is an obligation of people that have houses in contact with wildland fuels. They need to clean the vegetation in a radius of 50 meters around their homes. Also, the settlements, the villages, need to have a full break without vegetation of 100 meters around the perimeter of the villages. And basically this is it. The implementation is not always fully addressed, because many times people either don't have the money or they don't own the land or something like that. but it's mandatory by law, and well, that's it.
So it is a really excellent presentation, Professor Luís. So I have one question, like the most of the images that you have showed, they have this fluctuated topography, like with valleys and mountains. So are these wildfires frequently occur in these terrains, or is it specific to Portugal?
No, I mean, the steeper the terrain, the more complex the topography, the higher the probability to have extreme fire behavior in the fires, and the more difficult they get to be controlled. But you can have fires in any place as long as those conditions that I talked in the first slides are met. If you have fuels, topography, and the weather that allows fires to propagate, you may have fires. If those three conditions are met, no matter where you are, if it's flat, if it's a hill, if it's a canyon, you can have a fire, of course. One of the major drivers of fire is the weather. If you have a dry, hot weather, you are more prone to have serious problems with fire. That's why you see fires in Portugal, well, in the Mediterranean climate areas. You have South Africa, you have California, you have parts of Australia, you have Portugal, Spain, Italy, and Greece. So you see, the common factor among these countries I've said is the weather, which is more or less the same. Hot, dry summers and rainy winters where the vegetation grows a lot. And then you have another hot, dry summer. But it doesn't only burn in the mountains, it can burn in the flat terrains also.
Right. So, Professor, you use the word of compartmentation when in your presentation. So, actually, we are familiar with the compartmentation when it's come to the buildings. So, we know that buildings are separated into the compartment by building up fire-resistant structures. So, similar to that, are there any compartmentation method to forest fires?
So, what compartmentation meant in that slide was in terms of vegetation structure. I mean, not having a continuous area of the same vegetation without any breaks. So compartmentalize the vegetation so that it does not allow for the fire to propagate freely for a large area of terrain. Okay, so just instead of having large areas of vegetation, divide them into smaller blocks of vegetation.
Understood. Thank you.
So can I ask a question? Professor, thank you so much for the nice presentation. So what I want to ask is that although that these wildfires cause a huge amount of damage, we know that in some aspects they are beneficial too. So like for example, some plants do their propagation using wildfires. So in Portugal, is there any kind of a plan to have these control fires to help this the plant propagation and stuff, but not do like to prevent other damages? Do you have any plans to do this? Control fires and reduce the damage?
Actually, yes. I was telling the professors earlier, I also am a technician, a certified technician of prescribed burning. That's what we called it, to introduce the fire into the landscape in a prescribed and controlled way in certain conditions that are very different from what could be found in the summer. But it's in a very small proportion to what should be done or what could be needed in terms of the general picture in Portugal. So it's a very small part of the country that is being managed with fire, and it's I don't remember the numbers, but I know that it's clearly not enough. But yes, we have also, mainly in those areas where, for instance, the shepherds in the mountains, usually during the spring, winter, spring, they burn the land, the shrubs and the herbs, so that the sheep or the goats can have fresh herbs in the next spring or a couple of months later. And those sometimes would evolve to fires because they could not control them. So part of those prescribed burnings is done to replace those ancestral burnings of the shepherds. Another thing is to burn the vegetation in some sensitive ecosystems that need the fire to regenerate. A third objective could be simply to remove fuel in the mountains, mainly in the mountains, and in a more sustainable and ecological way than with heavy machinery or something like that. And at the same time, creating these discontinuities to compartmentalize, like I was telling before, and allowing to fires not to turn into very large fires.
Yes, thank you, Professor.
I have a quick follow-up question about the climate change. So what you said, like everything what you said, would intensify in El Nino years in certain parts of the world, as well as climate change predictions. So I guess you will be a busier man in the coming years, right?
Well, yes. I'm not an expert on climate change, but I can tell you that what we have been observed is that it's more frequent to observe extreme phenomena in the weather. So longer dry periods or warm or heat waves. For instance, now we are passing to, you say that you are having thunderstorms and heavy rain. We haven't seen
dry season.
We haven't seen rain in months, more or less. Just some drops here and there, and we are concerned about this drought period that will keep our water levels low in terms of usable water for the population. So heat waves are becoming more frequent, for instance, and this is due to climate change, in my opinion. There is no other explanation.
Yeah, thank you. And I think it's 3:30 here in Sri Lanka, and I guess 11 o'clock at Lisbon, correct? Yes.
No worries.
So thank you so much for this edition of really fascinating, very different talk. Yours is the most like extreme that we had in terms of the dimensions that we covered so far. Very, very thought-provoking and exciting. Thank you so much. I will hand over the podium to Dr. Maheshi Mapalagamage to do the formal.
Thank you very much, Professor Sampath. So thanks a lot, Professor Luís, for that informative and very excellent presentation, as Professor Sampath mentioned. I think we all learned a lot about forest fires and its impact on wildland and urban interfaces. And I'm pretty sure that this talk will open up novel field of research in Sri Lankan scientific community, and including our undergraduate students as well. So therefore, thanks a lot, Professor Luís, for your effort in educating us in this fascinating subject area. And I would like to thank Professor Deepthi Wickramasinghe for her continuous support given us throughout, because she's making these impactful collaborations, and the best thing is she's thoughtful enough to share them with us. So therefore, thanks a lot, Madam, for inviting and introducing Professor Luís to us. And I would like to thank Senior Professor Preeti Udagama, Head of the Department of Zoology and Environmental Sciences, University of Colombo, for her immense support in making this event successful. And I'd like to thank a lot to Dr. Sashini Amarasekara for creating this nice flyer, and Professor Sampath Selviratne, he arranged everything and he ran this session very smoothly. So thanks a lot, sir. And I'd like to thank the audience, especially because making these sessions lively and active by your active participation. And finally, I wish you, Professor Luís, all the very best. And please continue with this fascinating work. And we hope you will keep in touch with us. And with that note, I have a pleasant day, everyone. And I hope you all stay safe and happy. Thank you.
Thank you very much for having me.
Thank you, Luís. And
Okay.
we hope to see you one day in Sri Lanka.
Hopefully. Okay,
Okay,
thank you very
stay
much
safe.
for inviting me. Okay, it was an honor for me. Bye-bye.